It's 3 a.m. A critical machine on your production line goes down. You race to the control cabinet, frantically troubleshooting, only to find out the culprit is this: a blown fuse. You replace it, but you have no idea why and when it blew. What if you could diagnose, reset, and even prevent that failure right for your PLC without ever opening the panel door? Well, now you can. Welcome back to Control X Engineering. If you've ever had to run to the production line because of a blown fuse or breaker trip and wish there was a better way to diagnose and troubleshoot, then this video is for you. In this episode, we will introduce you to an innovative solution from Beckhoff Automation that helps us do just that by turning overcurrent protection into a smart, EtherCAT-enabled tool that tells you what went wrong and when, without requiring you to open the control cabinet door.
The EL9227 terminal from Beckhoff Automation. It gives you protection, monitoring, and control, all in one EtherCAT terminal. It's not just stopping faults, it's giving your PLC a new level of visibility into your system's health without ever using a multimeter. In today's tutorial, we'll do a complete technical evaluation and dive into its tech specs to see what makes this device special. I'll show you how to integrate it into your control system and how to configure it in TwinCAT to make use of all its diagnostics capabilities. So put that multimeter away and let's get started. In traditional designs, overcurrent protection in control circuits is disconnected from the control logic. Passive external protection devices like fuses or breakers are usually used for short circuit and overcurrent protection. The EL9227 is a 24-volt system-integrated power feed terminal with built-in electronic overcurrent protection capabilities from Beckhoff Automation. It eliminates those passive devices by combining overcurrent protection directly into the I/O layer. This means quick and easy installation, reduced costs and space requirements, easy and flexible on-site adjustment, as well as reduced downtime. In addition, the EL9227 features integrated monitoring and real-time diagnostics, data logging capabilities, and historical plant data. You get faster troubleshooting and better fault detection. The complete documentation for this device can be found at Beckhoff Infosys website. Before moving further, I would like to thank Beckhoff Canada for generously providing us with the EL9227 terminal that made this video possible. Before diving into the tech specs of this terminal, let's first understand the product naming convention. The nomenclature for this terminal looks something like this. This digit specifies the number of channels and whether it has standard or extended functions. Possible values are 1, 2, or 7. A value of 1 or 2 specifies the number of channels with standard functions, and a value of 7 specifies that it's a 2-channel device with extended capabilities. This is the code for the failsafe element for channel 1. Possible values are 4, 5, 6, and 9. This is the code for the failsafe terminal for channel 2. Again, possible values are 4, 5, 6 for the 2-channel terminal and 0 for the 1-channel terminal. The last 2 digits specify the rated current of the device for both channels. Possible values are 3, 4, 5, and 8. The number 9 is used to denote 10 amps. A 0 for these digits denotes that the nominal current is adjustable in 1 amp increments up to 10 amp max. Let's see a few examples. This is a single-channel overcurrent protection terminal with standard functions. This is a dual-channel overcurrent protection terminal with standard functions. This is also a dual-channel terminal but with extended functions compared to standard terminals. With extended functions, numerous process data variables are available. Measured current and voltage values are also accessed, which makes the EL9227 ideal for plant monitoring and facilities troubleshooting. Consider a few more examples with complete part numbers. This is a single-channel overcurrent protection terminal with standard functionalities and nominal current rating of 3 amp. This is a dual-channel terminal with standard functionalities and nominal current rating of 8 amp and 2 amp for channels 1 and 2 respectively. This one is a dual-channel terminal with extended functionalities, and current can be adjusted in 1 amp increments up to a maximum of 10 amp with TwinCAT, as well as by means of mechanical buttons on the terminal. Yes, this terminal has 2 illuminated push buttons, which we will see shortly. This is the part number I have in my possession and will be reviewing in this video. Before we discuss the Beckhoff terminal, let's first talk about why it's needed. Overcurrent protection, or OCP, is an indispensable safety measure in all electrical systems, designed to prevent the flow of excessive current that could damage equipment and pose a risk to operators. OCP serves as the first line of defense against 2 primary overcurrent conditions: overloads and short circuits. An overload is characterized by a gradual, prolonged increase in current beyond a circuit's safe capacity, such as a motor drawing excessive current due to heavy load. Conversely, a short circuit is a sudden and extreme surge of current resulting from an unintended, low-resistance path, often caused by damaged or faulty wiring. The ability of a protection device to quickly and reliably interrupt these conditions is critical to preventing costly damage, overheating, and potential fires. Industrial control circuits typically operate at 24-volt DC, with power supplied by a switched mode power supply. While these power supplies have their own integrated current-limiting features, this characteristic presents a unique challenge for conventional overcurrent protection. During fault condition, a large fault current can flow through the circuit, which causes the power supply's output voltage to drop below its nominal rated value. This voltage drop below the operational threshold of other connected devices leads to a system-wide shutdown and excessive downtime of the control circuits, including PLCs, sensors, relays, and other 24-volt consumers. This undesired condition can be prevented by implementing overcurrent protection devices. For 24-volt circuit protection, fuses are a simple and widely used form of overcurrent protection. They consist of a thin filament or metal strip that melts when the current exceeds a certain value, thereby interrupting the overcurrent condition. While fuses are reliable, their single-use nature introduces several significant drawbacks. A blown fuse must be physically replaced, which requires a stock of spare fuses and adds to operational cost and expensive downtime. In addition, there is no direct feedback to the PLC or the higher automation system. This is exactly where the Beckhoff's EL9227 shines. It is a 24-volt DC EtherCAT terminal with an electronic overcurrent protection function. The EL9227-5500 is the 2-channel version with extended capabilities and switches to 24-volt DC overcurrents off reliably. With extended capabilities, numerous process data are available, like measured current and voltage values. The operating status is also displayed via an LED on the terminal and also through the process image in the PLC, as we will see next. Let's look at the physical device first. The nominal current can be set in 1 amp steps up to a total of 10 amps combined, either through TwinCAT or via the mechanical push buttons on the device itself. In addition, there are further versions of the terminal with fixed nominal current for each channel. As with other Beckhoff terminal, the top part has the LED indicators. The run LED indicates the EtherCAT operating state of the terminal. The ready LED indicates the status of the overcurrent protection programming mode and query mode. Green means the 24-volt DC supply voltage is present and initialization has completed. Overcurrent protection is active and operation mode is also active. Orange means the device is in programming or query mode. Solid red means it's missed 24-volt supply voltage or the device had an initialization error. If it's flickering red, that indicates wire break or other incorrect wiring conditions, such as wrong ground reference, for example. These two status LEDs show additional information for the outputs 1 and 2. Solid orange indicates that the corresponding output has detected under voltage or over voltage. Flashing red indicates cooling phase and is currently active for that output. The EL9227 terminals have 2 illuminated push buttons, one for each output channel. These push buttons allow switching the outputs on and off and also resetting the respective output after it has tripped. The outputs can be switched on or off by pressing the corresponding push button. This function can also be done from the PLC using the corresponding PDO mapping, which we will see later in this tutorial. The 24-volt supply is connected to the in-feed connection points 2 and 3 as shown here. Points 5 and 6 are internally connected to points 2 and 3 respectively as shown. These are the 2 protected outputs on the EL9227. These outputs can be accessed by connecting to the connection points 5 and 8 as shown here. The same protected output 1 is also available via the power contact rails of the terminal. This way, the adjacent EtherCAT terminal placed to the right side of the overcurrent protection terminal are supplied with a protected 24-volt. This means if you have a digital output terminal placed next to the EL9227, the supply for the digital outputs is protected by the output 1 of this terminal. This terminal also features 2 digital input channels, which use the terminal's in-feed 0-volt as the reference. These digital inputs can be used for both switching as well as resetting the corresponding output. They do the same function as the 2 illuminated push buttons on the terminal. Alternatively, the outputs can be switched and reset programmatically from the PLC. So there are 3 ways to switch and reset the protected outputs. Here's an example circuit showing an external push button connected to digital input 1 for switching the output on an EL9221 terminal. This load is now protected against overcurrent and short circuits and uses the push button connected to the digital input as a reset. Let's review some of the key technical specs of the EL9227 terminal. This table lists some of the key details about this terminal. The nominal voltage is 24-volt DC. Nominal current rating is 10 amp maximum with adjustable limits for both channels in steps of 1 amp from 1 to 10 amps. The max of 10 amp can be split between the 2 channels. Maximum current input draw is 10 amps. The undervoltage pre-warning can be adjusted between 17 and 24 volts. The output pre-warning limit can also be adjusted between 50 to 100%. This terminal uses 80 milliamps for its own operation and draws this directly from the E-bus supply. It reports the input and output voltage as well as output current, and these are the typical measuring errors you can expect. Typical restart time is about 10 seconds. This restart time depends on the internal temperature of this device. If the temperature rises, the restart time increases accordingly. This specification refers to the internal power dissipation of the terminal. The EL9227 has 3 modes. The operation mode is active as soon as the terminal is supplied with supply voltage. The initialization has been successfully completed and no other mode is active. This is effectively the normal mode of operation for this device. The programming mode is available for adjustment for the adjustable overcurrent protection terminals like the EL9227-5500, the one that we are working on. To enter this mode, press and hold one of the 2 buttons in the operation mode for more than 3 seconds. In programming mode, both outputs can be set up simultaneously. The query mode exists for the fixed overcurrent protection terminals, so not this terminal. So this mode is not available on the adjustable EL9227-5500, but other variants of the EL9227 with fixed ratings have this mode. This mode is intended for querying the nominal current value. To enter this mode on a fixed OCP device, press and hold one of the 2 buttons in operation mode for more than 3 seconds. This table shows how the buttons work in operation mode. Briefly tapping the button switches or resets the respective output. Doing a long press activates the programming mode or query mode depending on the terminal. For this tutorial, we'll focus on the configuration using TwinCAT rather than through programming mode, so I'm not going to go into any more detail than this. One important point to keep in mind is if settings are changed during the operation while outputs are switched on, the outputs remain unaffected. This has the advantage that the system can remain in operation and a change can be made online without switching off the output. The EL9227 terminal is equipped with open load detection. This means that it checks for possible wire breaks at its outputs. This function is available when the output is switched off. This table shows the default factory setting for the EL9227 terminal when commissioning for the first time. Let's look at the terminal wiring for use as an overcurrent protection device. The supplied 24 volt and 0 volt are wired to connection points 2 and 3 as shown, with optional normally open push buttons wired to digital inputs 1 and 2. These push buttons control the switching of the respective outputs. Here I show a load connected to output 1, which is now protected against short circuits and overcurrents up to any desired current level up to 10 amps. If more than one load is required, then use terminal blocks for power distribution. Alternatively, we could also use distribution terminals like the EL9185 from Beckhoff. This terminal provides 4 connection points each for both 24 volt and 0 volt. In this example, the protected output 1 from the EL9227 terminal passes to the distribution terminal through the power contacts on the side of the terminal, and now accessible through the connection points on the EL9185. Output 2 is accessed directly from the EL9227 as shown for channel 2. Now let's see how to commission this terminal in TwinCAT 3. I will be using my CX5140 IPC for the PLC runtime, and I have installed the EL9227 and the bus end cover as shown. After scanning the hardware, we should now see the EL9227 added to our I/O configuration. If you're finding this tutorial helpful, then please take a moment to subscribe to the channel if you haven't already, and also hit that like button to help grow this channel. Now let's get back to reviewing the configuration in more detail. Let's expand the terminal to see the available process data. As we can see, there are input and output PDOs, which are available for both overcurrent protection channels. As a recap, PDO refers to process data objects, which are cyclically transmitted process values. Such objects can either be individual variables, such as voltage or current value, or they could be a structure or group of variables, as is the case here. Expanding the PDO will reveal the PDO contents. The individual PDOs can be activated or deactivated separately in the Process Data tab by checking or unchecking the required PDO assignments. In this case, I have selected the outputs in the Sync Manager, which allows the 2 output PDOs shown highlighted in blue. PDO 1600 contains the outputs for channel 1, and PDO 1601 contains the outputs for channel 2, as you can see in the PDO list table. By default, both input and output channel PDOs are selected, so there's nothing more to do here. Expanding the PDO for input channel 1 reveals its contents. We have a structure containing status data and individual data for load, current, and voltages. These are all represented by 16-bit unsigned integer data types. Load is the percentage load current seen by the device based on nominal current or set fuse value, represented by I sub n. This is the measured current on the output channel in units of 0.01 amp. These are the input and output voltages reported in units of 0.1 volt. Expanding the status structure shows all the status bits. Here's a table with description of the status bits taken from Beckhoff Infosys website. Feel free to pause to look at it. Here you'll find information about the channel status, like if the channel is switched on or if it's tripped due to short circuit or overloaded, and other useful info like over voltages, under voltage, etc. Next, let's look at the outputs which are related to controlling the behavior of the OCP terminal. Here we can see the two control bits for reset and switch. These bits function the same way as the physical push buttons on the terminal and allows us to reset and switch the output programmatically from the PLC or HMI. Next, I'll show you how to adjust the settings for the overcurrent protection functions of the terminal. For that, double-click on the terminal and navigate to the COE Online tab. The parameters of interest are at index 8000 for channel 1 and index 8010 for channel 2. Alternatively, for newer terminals, there's a settings tab that allows us to change the settings for both channels. So let's take a look there. So this is the settings page, which contains all the adjustable parameters for the overcurrent protection functions. The settings on this page are grayed out and disabled by default, and can be enabled by clicking this checkbox and confirming the pop-up message box with OK. In the general section on top, we can make the channel selection and change the mode of operation, which is available for my terminal since it has extended capabilities. The choices are standard mode or compact mode. The mode selection changes the PDO contents for the inputs. In this example, I've selected compact mode for channel 1 and standard mode for channel 2 to show you the difference in the available process data objects that can be linked to the PLC. This section provides status information about the terminal. The parameters section is where we can adjust the overcurrent protection settings like trip current settings, warning thresholds, and characteristic curve settings. For the characteristic pre-select parameters, we have choice of selection between standard, fast, slow, or manual. After modifying the configuration, click the Apply Online button at the bottom to write the modified parameters to the terminal. Next, let's link the process data to the PLC to be able to control the overcurrent protection output channels through PLC logic. The conventional way is to create corresponding variables in the PLC, usually declare them in a global variable list like using @i star and @q star, and then linking those individual variables to the corresponding inputs and outputs of the device. In this case, we would need to declare 4 inputs and 2 outputs for each channel. And I haven't even created the multiple Boolean variables for linking all the status bits because this is not an efficient method. I will show you a more versatile way to link the terminal's inputs and outputs to the PLC without having to declare all these variables and still have access to all the device data and control functions. Back on the device, in the I/O node, navigate to the PLC tab. Here, click on Create PLC Data Type checkbox. A custom data type is generated and displayed in the data type field, which can then be copied using the copy button. Now back in the PLC, we can create an instance of the copied data type as shown. Build the project to make the instances available for linking. After build completes successfully, click on the Link to PLC button. In the pop-up dialog box, select your PLC variable and click OK. The PLC variable is now linked to the device, and the device should now be fully accessible from the PLC. Since the linking is now complete, all that's left to do is activate the configuration to transfer the settings of the development environment to the runtime system. If you look at the device's inputs and outputs, you will notice small overlay icons on the data objects, indicating that they are now linked to the PLC. We should now be able to access them in the PLC using the linked variables. Let's take a look. In the code section, you can either use the input assistant by hitting the F2 key on your keyboard and navigating to the variable section and find our variable, or you can type it out manually and should now have access to the inputs and outputs for both channels, including all the status bits. And now let's hop onto TwinCAT to see how easy it is to set up and commission the EL9227. And to show the capabilities of this terminal, we will also install an EL2809, which is a digital output terminal, to show how to use the protected output channel 1 of the OCP terminal. I will connect 2 relays to 2 separate channels of the EL2809. The digital outputs of this terminal will now be powered through the protected output of channel 1 of the OCP terminal. Similarly, I'll connect another load to the second channel of the OCP terminal. To test the capabilities of the OCP terminal, I will intentionally create fault conditions on load 2 here and on one of the relays here, and we'll see the behavior of the OCP terminal. I have TwinCAT open, so let's start by creating a new project. We'll do TwinCAT projects, and I'll call it let's switch to our target system. In the search bar, I can do a broadcast search, and I'm connected to this adapter, so I'll unselect the others. So my CX5140 is detected, and I have already previously connected to it, so I don't need to do anything. In your case, if you're not connected, check this radio button and hit add route. Once the route is added, you can close the window, and here select your routed IPC and click OK. So now we are connected to the IPC. Next step is to go to the IO devices and right click scan. So hopefully it should detect my EL9227 and the 16-channel digital output term. I'm going to select the first device and click OK. Scan for boxes, yes. You can say no to this. And let's expand this. So there's my EL9227 and my 16-channel digital output card. So let's configure the OCP terminal first. We can go to settings and enable these settings. So here it's asking you to check that the firmware version is greater than 1. So let's cancel this and go to COE online. And here you can see the software version is version 5. So we are good. So we can go here and check this box. Say OK. So this is the entire settings, the apply online buttons at the bottom, which we have to hit in the end. So here we have the 2 channels. I'm going to set the current limit to 2 amps for channel 1. And for channel 2, I'm going to do 1 amp, and under characteristic, I'll make it fast. You can come down and apply. Takes a few seconds. Okay, it's done. Next step is linking this to the PLC. We can go to the PLC tab, check this box, and I want to do per channel. So that means we have to create 2 variables to link to each of the 2 channels. So now you have your 2 channels here. It's the same data type. So let's copy this. And now we can create a new PLC. PLC is created. I would like to make a new global variable list, so we can do add GVL. I don't need this for the demo. So here we'll create our 2 channels. So I'll say channel 1 of this data type. Similarly, I'll create my 2 digital output channels. Next, we can do a build. As you can see, there's nothing under the instance, so these variables are not exposed to the outside of PLC. After you create variables, you have to do a build. Now it creates the input and output instances. Good, so now we can go back to our OCP terminal, link to PLC. So I have channel 1 selected, so let's link that to the channel 1 variable. Select channel 2 and link to the channel 2 variable. And that's all there is to linking this to the PLC. Next, we have to link the output channels on the EL2809 terminal. So let's expand to channel 1 output. Right click, change link. Here's my channel 1 variable. It's a good idea to check these 2 boxes. And it's linked and it's taken over the name. Similarly, channel 9 for the other one. Now all that's left to do is reactivate configuration. So our icon turns green and we are activated. Now that we have linked to the PLC, we can go to the PLC and log in. And here we should be able to see all the inputs and outputs for our 2 channels on the OCP terminal. Let's look at the inputs first. This is input on channel 1. I'm getting a voltage in. So this is the input voltage times 10. So this is actually 24.1 represented by unsigned integer. The output voltage is 0.7 volts. Let me just take a look at the LED on the EL9227. Yes, these are turned off. I can physically turn this channel on by pushing the push button on the device. And yes, so my channel 1 output is on and we can see it's reporting 24.1 volts. I'm going to turn it back off. Let's try to control it from the PLC now. So here's my switch. And that is the same thing. So it's only looking for a rising edge. We can set it back to false. Now, if there's a fault, we'll have to reset it using this bit and then switch it back on using the switch. Let's see what's under the status. So here it's showing my channel is enabled. I have no faults. The load is 0, current is 0. I'm going to connect a load to it now. So as you recall from the presentation, the channel 1 powers the outputs for the EL2809 terminal. So let's fire these 2 outputs. As you can see, it's reporting some current and it's loaded to 2%. Let's look at the second channel. On this channel, we can turn this on. I have a bigger load here, so we can see the load and the current. This one I can actually create a fault by creating a short circuit condition. So let's do that. But before that, let's expand the status and see what happens. So it's tripped. There's a cooldown lock and now it's false. You have to wait until the cooldown lock becomes false before you can reset it. I have removed the short circuit condition, so I should be able to reset. And my output is enabled, all the fault trips are gone. Let's see that again. So I've tripped it. I'll try to reset it right now. It's not going to reset. We have to wait until the cooldown period has expired. And we are able to do it now, and my load is back up. My output voltage is 24 volts. Now what happens if there's a short circuit condition on the first channel? Remember, it's powering my EL2809 outputs, and I can see my relays are currently closed. I'm going to do a short circuit condition on this channel on the device itself. Okay, so I was able to trip it. The output voltage is dropped. Now, even though my output bits for the 2 channels on the EL2809 are still set, I can see the LED on the terminal is still on. Let's go take a look at the terminal. Let's put them side by side. So channel 1 is still on, channel 9 is still on, but my relays are physically turned off because there is no 24 volt passing from overcurrent protection terminal to the EL2809 because of the short circuit condition. Now if I reset the faults, yes, so now my outputs are enabled, and I think you must have heard the relay and contactor just closed. So that's all I wanted to demo on the EL9227-5500 Overcurrent protection terminal. Hope you guys found this tutorial useful. So that's how easy it is to use the Beckhoff EL9227 Overcurrent protection terminals, which provide programmable and repeatable protection. Unlike a fuse that must be replaced after a fault, the EL9227 provides an electronic trip that can be configured and reset automatically or through logic, which keeps machines running and reduces manual intervention. Some of the practical benefits I see in my circuit design are: with remote control and diagnostics, I can clear transient faults from the PLC, which means fewer service interruptions. No need to stock many fuse types for the same panel. Adjust the EL9227 in software instead. Trip reasons and measured values are logged and visible in the control system, which helps root cause analysis after faults. Contactors, sensors, and I/O modules often tolerate short inrushes but needs precise overload protection. Programmable electronic protection handles the nuance better than fixed fuses. I use the EL9227 because it turns protection from a passive, one-time safety device into an active, observable, and configurable part of the control system. For modern 24-volt automation where uptime, diagnostics, and tight integration matter, the EL9227 reduces downtime, simplifies wiring, and gives me the data I need to design smarter systems. Thanks for watching. If you found this video helpful, then please like, share, and leave your questions or suggestions in the comments. I have a lot more content lined up for the new year, so be sure to subscribe so you don't miss out.